Welcome back to multivariate calculus. In this video, as the title above me says, we're going to be looking at limits and continuity. Finally, this far into the course, we're looking at something that actually sounds like calculus. When you first started studying calculus of a single variable, you learned a nice definition for the limit of a function, and you used that definition to come up with the continuity requirement for a function. And our goal here, if I get my head out of the way, is to take those definitions and repurpose them for functions of vectors. So remember, for a function in the real numbers, we have this definition. We say that the limit as x approaches c of f of x is equal to L if and only if for every epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus c is less than delta. A nice, easy to remember definition, I'm sure. I always found it easier to remember by thinking about the picture. If I've got a curve here, y equals f of x, I've got a point C, and I've got a y value L. The theorem tells me that if I pick a distance here called epsilon, that no matter what, I can find a box here of distance delta so that my curve goes out the left and right side of the box, not the top and bottom. All right, that's what the limit definition says. No matter how tall you make the box or how short you make the box, there is always a width that you can set the box where the curve goes out the left and right and not the top or bottom. That's all we're trying to say here. And for a vector valued function, we want to say the same thing. And so we will say the same thing. Right? Instead of the limit as x approaches c, it will be the limit as t approaches c because we usually use r as a function of t. Limit as t approaches c of r of t is equal to, well, L doesn't quite make sense because it's not a point anymore, it's a vector that we get out. So let's call it vector v. If and only if for any epsilon greater than 0, there exists a delta greater than 0 such that, well, the distance between two vectors, we don't use absolute value bars to denote the distance between two vectors. We use the norm of r of t minus v. But the definition is almost identical. Right? We've got norm instead of absolute value, and we've got vector instead of a point. That's the only difference. Everything else is exactly the same. and a whole bunch of technical language that I don't care to write down. Assuming that x, y, and z are all functions and the limits of all of those functions are defined at t equals c, then the limit as t approaches c of the vector valued function x of t I hat plus y of t j hat plus z of t k hat is equal to the limit as t approaches c of x of t I hat plus the limit as t approaches c of y of t j hat plus the limit as t approaches c of z of t k hat. Right? I've labeled this as a theorem. If something is labeled as a theorem, that means it needs to be proven. So I am going to prove this, or at least a subset of this. Like I said, the language that I've used here isn't entirely consistent. I'm assuming that these limits of the scalar functions all exist. So in my proof, let's define the limit as t approaches c of x of t is equal to Vx, that the limit as t approaches c of y of t is equal to Vy, and the limit as t approaches c of z of t is equal to Vz. And so what we want to show, remember, I don't think I've used it in this course yet, WTS is a nice abbreviation for want to show. The idea there is we've introduced some new language, we've introduced some new variables, and we want to make sure that we're going in the right direction. So I'm not claiming that this is true yet. I'm claiming that we should get this in our derivation. We should get that for r of t equals x of ti plus y of tj plus z of tk, and vector v equals vxi plus vyj plus vzk, that the limit as t approaches c of r of t is equal to v. Right. The only tool we have for working with limits on vector valued functions is the epsilon delta definition, which means that we will have to use the epsilon delta definition in order to make this proof. This is the first, last, and only time we will need to use the epsilon delta definition of the limit of a vector valued function in this course. Not the last time we'll need to use an epsilon delta definition of any limit, but at least of this particular one. But it is important to see that it works and it's not just something that we are claiming. It has to occur naturally based on a very natural definition for this extension of a limit. But let's start by letting epsilon be greater than 0. And whenever we do an epsilon delta proof, we go off to the side and do some scratch work. Our end goal is to show that the norm of r of t minus v is less than epsilon. That's the same as the norm of, if we go into components, this is x of t minus vx, y of t minus vy, z of t minus vz, is less than epsilon. And to take the norm of a vector, we're going to take the square root of the squares of each of these components. So we'll take the square root of x of t minus vx squared plus y of t minus vy squared plus z of t minus vz squared. Still less than epsilon. I know I'm kind of running out of space on the right-hand side of the screen. Sorry about that. But I'm also going to make the assumption, and we'll see why we can make this assumption a little bit later on. But let's make the assumption that each of these is equal to each other. And so we have the square root of 3 times x of t minus vx squared is less than epsilon, which means that the square root of x of t minus vx squared is less than epsilon over the square root of 3. And the square root of something squared is the absolute value of that thing. And that gives us this epsilon over square root of 3. All right, that's our scratch work. That's stuff off to the side. But there's always some scratch work that a person who is writing a proof is hiding, and then this magical thing shows up. In this case, it's going to be epsilon over the square root of 3. And since we know that all of these limits on the real valued functions, x of t, y of t, and z of t exist, there must be a delta such that whenever absolute value of t minus c is less than, I can't apparently write a delta. Whenever that's less than delta, we have that the absolute value of x of t minus vx is less than epsilon over the square root of 3. The absolute value of y of t minus vy is less than epsilon over the square root of 3. And the absolute value of z of t minus vz is less than epsilon over the square root of 3. All right, hold on a second. Let's make sure that that makes sense, because that doesn't quite follow the definition of a limit. I've done a little bit of hand waving here, but it should make sense once we stop and talk about it. I can pick any positive number that I want. In the definition, I called it epsilon, but here in the practical application, I'm calling it epsilon over the square root of 3. And for the first function, x of t minus vx less than epsilon over square root of 3, there is some constant delta whenever t minus c is less than delta. That's true. For y of t minus vy, there's going to be a different positive number delta, and for z of t minus vz, there's going to be yet another positive real number delta. But again, thinking about this visually, the purpose of delta is to define how wide the box has to be, or how wide the box can be, so that the function goes out the left and right of the box and never the top and bottom. If I've got a function where if I make the box this wide, it's going out the left and right, and then I narrow the box, it's not going out the top and bottom anymore, Now that it's narrower, it's even more constrained than it was before. And so I can choose the smallest value of delta that works for all three of these, right? I find the delta for each one that the definition of limits says exists, and then I pick the smallest one, and that's what I use here. All right, so that's the definition of a limit. Then from here, we go through our scratch work kind of backwards, and that gives us the rest of the result. Right, the absolute value, or I guess the norm of r of t minus v is the same thing as the square root of x of t minus vx squared plus y of t minus vy squared plus z of t minus vz squared. All right, we showed that in a couple of steps in the scratch work, but we just can reuse that here. And then each of these in turn is less than epsilon over the square root of 3. And if I simplify this, I have epsilon squared over 3 plus epsilon squared over 3 plus epsilon squared over 3, which is epsilon squared. And since I know that epsilon is bigger than 0, right? That was what I said way up here. Anytime you're doing an epsilon delta proof, the first thing you write down is let epsilon be bigger than 0. And since epsilon is bigger than 0, the square root of epsilon squared is epsilon. And so we found that this satisfies the definition. And with that, we can breathe a huge sigh of relief. Because what we just learned is that we don't have to do anything new with limits whatsoever. All of the tools that we already know how to use for limits, we can use for each component in the vector valued function on its own, and everything will work fine and nothing weird happens. That is fantastic. So if I want to take the limit as x approaches 1 of the vector valued function with components x squared, x minus 1 over x squared, and x squared minus 1 over x minus 1, well, plugging in the value of x equals 1, I would get 1. I would get 0 over 1 squared, which is 0. And then I would get 0 over 0, which is indeterminate. So this last bit is the thing that I'm going to look at a little bit more closely. The limit as x goes to 1 of x squared minus 1 over x minus 1 is the same thing as the limit as x goes to 1 of, I can factor that numerator into x plus 1 times x minus 1 over x minus 1. And the x minus 1s cancel each other out. So we're looking at the limit as x goes to 1 of x plus 1, which is 2. Right? Nothing new here. It is exactly the same process of working with limits that you've learned in the beginning of calculus of a single variable. We went a long way to show that nothing weird is happening, but we've gotten here and now nothing weird is happening. All right, and Just like we learned in calculus of a single variable, the purpose of limits is to show continuity. So let's take a look at the definition of continuity that you learned for functions of a single real variable. And let's look at how that turns into a definition for continuity for a vector valued function. Again, it's going to be basically the same thing. So for a function f, mapping from the reals to the reals, and there were three criteria. The function had to be defined at the point, the limit has to exist at the point, and those two results have to agree with each other. And there is absolutely no reason we can't just use the exact same thing for continuity of a vector valued function. So for r of t, mapping from r into, we could go into 2 dimensions, but we'll go into 3 dimensions because that's usually what we want to do. We say that r is continuous at t equals c if and only if r of t exists, the limit as t approaches c of r of t exists, and the limit as t approaches c of r of t is actually equal to r of c. It is the exact same definition of continuity that we had before. I mean, not exactly the same because it's a slightly different meaning of limit, but it is the exact same definition. I'm actually not going to do anything with this definition of continuity. We have it. You know how to deal with continuity for a function of a single variable, and nothing has changed. Except that continuity isn't as useful here. For a parametric curve, continuity doesn't give us everything that we want anymore. And so we're going to look at something a little bit more stringent, a little bit more specific that exists for parametric curves. Left out a term in there, sorry about that. Right, the curve is smooth at a point t equals c. if and only if x prime of t, y prime of t, and z prime of t are each continuous at t equals c and not all zero. All right. This definition of a smooth curve is going to be the valuable tool for us. Having functions with I still left the word out. I'm sorry. All right. The vector value function does still have to be continuous. We need continuous vector valued function and then more things. So on top of having a continuous vector valued function, we need to have the derivatives of each of the components of the function are continuous, and the derivatives of the components are not all zero. Some of them can be zero, but if they are all zero, you end up with weird motion. That's another one that's a little bit hard to see except through graphing, because the curves will still exist and they'll still look nice. But if you track the movement of a point, you'll see that it does some skittering and jittering that we don't really want. All right. So I think the best way to understand this is to look at something that breaks all of these rules. All right, let's start off with R1 of t has components t, t squared, and 1 over t. And I hope that you can see without doing any work whatsoever that this curve is not continuous at t equals 0, so it's not going to be smooth. And let's just write down the second one I'm going to analyze while I have the page up here. And let's go ahead and look at helps if I write down the right thing. I'm looking at the derivatives, not the thing I want to write down. Let's go ahead and look at t squared, t cubed, t to the fourth. All right, so that curve is going to give us something that is a continuous function, but it's not smooth. And so let's take a look at these two graphs to start to analyze the difference. All right, so here I have the curve t, t squared, 1 over t. And if we look at this curve and we kind of look around in various places, you can see that we've got two curves that are not well attached to each other. Although if I spin this around and look at the projection in the xy plane, it looks like a nice parabola. Right? The xy projection looks nice. But then if you tilt so that you can see what is happening in the z direction, you discover that there's a problem because those two ends of the parabola that looked like they were so nice aren't anywhere near each other in three-dimensional space. And so it's exactly what we expect to see with a discontinuity. It's exactly what we expect to see with a 1 over x kind of discontinuity. All right, let's take a look then at the other one that we wanted to look at. That was t squared, t cubed, t to the 4th power. And here you see a new kind of weirdness going on, because if you look at this curve, it looks kind of pointy. And let's zoom real in on that origin. Really focus on the cusp that we end up with here. Because that's what we're talking about when we're saying smooth. Right? Just like when we talked about smooth curves in 2 dimensions as being curves that didn't have these weird cusps happening. Just the fact that those derivatives are all 0 at that point allows a point, a cusp, to happen. And so we can think about the parametric curve. We can think about it being continuous. We can think about whether or not it is smooth. And we're going to take and extend these ideas and start building into some of the other things that we've done with calculus, starting in the very near future. But for now, let's just focus on this. We now have conditions for limit, for continuity. And so thinking about those things, I want you to take a look at another vector valued function, which is not going to be smooth. And I want you to graph it and then tell me why it's not smooth. All right, so take a look at the vector valued function. R of t equals t minus 5, t, absolute value of t minus 5. I would like you to graph this parametric curve using GeoGebra or other software of your choice. Identify in the graph that it is not smooth at t equals 0, and then talk about why it's not smooth using the definition of a smooth curve that we were just talking about. See what you can do with that one, and I'll see you in the next video.